Okay, in the previous YouTube we talked about a ramp without friction, and now we're going to consider one with friction. And so we can basically use exactly the same um, approach, sketch, with the exception that we're going to add a friction force pointing up the plane here. And so I've got three cases worked out here. First of all, our Newton number 2 in the y direction is going to be just exactly what it was before. And if we solve that for n, we're going to get n is equal to mg cosine theta, which, as you recall from the previous YouTube, means that the normal force is less than the weight, since cosine theta is less than 1. The Newton number 2 in the x direction is now going to be just what it was before, but we're going to have to subtract a minus f sub f on the left-hand side for our net force. Previously it was just m sine theta, now it's mg sine theta, now it's mg sine theta minus f sub f, because f sub f is pointing up the plane, so we're going to bookkeep that with a minus sign consistent with our coordinate system. So if we take this equation and we solve for a sub x, and we substitute for s sub f, we substitute mu times mg cosine theta. So mg cosine theta is the normal force, so here's mu times n, which is always what friction will be. We can cancel out some m's, factor out a g, and get that a sub x is equal to g times sine theta minus mu times cosine theta. Now notice I haven't filled in whether it's mu sub s or mu sub k, because that depends. And so let's do three cases here. Let's do, just in summary, what I'm going to do is I'm going to do a case where the angle is shallow enough where m does not slide. Number two, where the angle is just at the cusp of sliding occurring. And number three, where we are at a large enough angle where there's acceleration of m down the plane. So let's start with number one. Let's assume that mass m is equal to 2 kgs and that mu sub s is 0.10 and mu sub k is half of that, 0.05. And let's say that we have an inclination of the ramp with respect to the horizontal of 5 degrees. That would be considerably less than what I show in this picture here. And so in that case, what we know is that the maximum frictional force possible from static friction is mu sub s times the normal force, which is mg cosine theta. So if you put the numbers in, that's 0.10. That's what we're assuming for mu sub s here. Times mg, well, that's the weight. I'm using easy numbers here. 20 newtons. And then 5 degrees, well, that would be cosine of 5. And if you do the numbers here, you get 2 newtons. 0.1 times 20 is 2, and cosine 5 is so close to 1 that we're just going to say 2.0. In the meantime, mg sine theta, which is mg sine theta represents the force down the plane. It's the component of the weight down the plane, is 20 mg, 20 newtons, the weight of the object, times the sine of the angle, which is 1.7 newtons. And since the force down the plane is less than the force up the plane, the friction supplied will cancel this out. It can go up to a maximum of 2. It will simply supply 1.7 newtons going up the plane. And a sub x will then be 0 meters per second, and therefore m will not slide. It'll just stay there. And so at this shallow degree with the numbers that we assume here, m is going to stay put. All right, so in number two, what I do, and this is perhaps the most interesting calculation on the page here, is let's find the angle at which it just begins to slide. And so for that to occur, I need to have the force down the plane equal to the maximum possible friction supplied by static friction up the plane. And so at that angle, you're just on the cusp of the mass beginning to move down the plane. And so this condition then, we can, as you can see, we can divide by mg. The mg's cancel on both sides, and then I can divide by cosine theta. Okay, so as an aside here, and I'll write this down, you should realize that tangent of theta is equal to sine theta over cosine theta. I'm using that fact here. So tangent theta is equal to mu sub s, using this and canceling mg's on both sides. And now we can solve for theta by taking the inverse tangent of mu sub s, which in our case is 0.1. And the inverse tangent of 0.1 is 5.7 degrees. And so when we chose 5 degrees here, we just needed to go a little bit less than 1 degree beyond 5 degrees, and it would start sliding. And so at this point, at an angle of 5.7 degrees, m will just begin to move. For the third case, let's go beyond 5.7 degrees, where we know acceleration will occur now. And so we are definitely going to have a positive a sub x in that case, and that means we have to use kinetic friction. And then a sub x then is going to be this expression right here, g times the quantity of sine theta minus mu sub k. I know it's moving, so I have to use the coefficient of kinetic friction times the cosine of the angle. And let's go ahead and put the angles in here. 10 degrees. Sine of 10 minus 0.05. That's the coefficient of kinetic friction times the cosine of 10. And if you work this factor out in parentheses multiplying g, that turns out to be 0.12 times g. Since g is pretty close to 10, that's going to be pretty close to 1.2 meters per second.